I'm Patricia Dailey, Associate Professor of English and Comparative Literature at Columbia University. And I am a medievalist, but I also work on contemporary philosophy, and I'm especially interested right now on trees, which is part of a new book project. And I'm here to speak with my old friend and colleague Vincent Fleury.
Hello, so I'm Vincent Fleury from Paris. I'm a directeur de recherche, so it's something like senior scientist at the French CNRS, which is the government agency for research. And I actually work at the Université de Paris Cité. And I am a physicist, but I study developmental biology, especially the early stages of embryo, even human embryo development. And I have also written a number of books, a few novels and a few popular science books.
So you've written a number of books, both you have an interest in literature, you've written on Henry James, you've written mystery novels, you've written children's books, and you've also written very important scientific articles and books, one of which, or several of which, are particularly interesting. Arbre de Pierres, Trees of Stone, on fractals and growth in matter. But also your work that's recently appeared, I hope we get a chance to talk about. But I want to start with a quotation from the book Branching in Nature, which you both contributed to and I guess you edited. When you say, when Galileo Galilei stated that the geometry of nature was written in terms of planes, cones, and spheres, he missed one essential pattern of nature, the tree. Voilà.
Yes, it's true that, as far as you can read in the history of science, you see that people have stumbled on trees, have seen trees, have observed trees, and they have repeatedly associated trees of stone, what we call dendrites, with trees which are more classically seen in biology. And people have wondered about, for example, corals, which are also trees, but they are more animal-like. And so people have thought that maybe there is some sort of a general pattern, universal pattern, which would be trees, independently of their ontology, independently of whether they are living stuff or minerals or plants or animals. And so this idea that branches are maybe universal have sort of disappeared in early times of the modern science because of the specializations of the disciplines. People have started to study plants, so they studied trees in plants, and then people have studied animals, so they have studied sort of trees in animals. Maybe lungs are trees, kidneys are trees, but in animals. And it's only recently, by the end of the 20th century, that a number of scientists have started again to consider branches as some sort of universal pattern, and that maybe it was possible to gather inside a common language or a common science the study of all these branching things. So that started in the 1980s, maybe by the work of Len Sander, around dendritic growth. Mm-hmm. So dendritic growth in itself is a bizarre word because it uses the Greek word dendron, which means tree, but dendritic growth, it's nothing like trees. It's always minerals. Dendritic growth describes the growth of branches in minerals, and so people started studying dendritic growth, and especially there was one very fashionable system which was electrochemical dendrites, and it turned out that electrochemical dendrites, which are mineral dendrites, which were a curiosity since the time of ancient alchemy. Alchemists used to grow electrochemical dendrites. They were very keen at growing electrochemical dendrites. It suffices to mix a number of solutions to get these mineral dendrites. So this is a very famous experiment which is found in very ancient books, repeatedly in Middle Ages and more classical books. But it turns out that this experiment of electrochemical growth happened to be very important in industry because electrochemical dendrites grow in electric vehicle batteries, and this is why you don't have cars which have a capacity to an autonomy larger than 500 or 700 miles. It's very difficult to make cars which have an autonomy larger than 500 miles because you have little trees, really trees, which grow in the batteries, and this is why the batteries of electric vehicles tend to explode, and this is why you have these fancy videos on internet of cars which burn in the street. It's because of explosion of the battery related to little metallic trees. So the good point is that raised the interest in branching at large, and a great number of scientists like myself joined a bandwagon of people who started to study branching in physics and branching in biology with the same concepts, the same tools, and voila.
Thank you. So that leads me to my next question about the difference between the human and the plant. And according to somebody like Emanuele Coccia, as I mentioned before, on his book, where did I put the book? Voila. The Life of Plants and Metaphysics of Mixture, he thinks of our own givenness, or our own, to use a Heideggerian term, thrownness in the world, that the fact that we, like plants, we absorb oxygen, we expire, we're very much a part of our organic universe. We are organic beings, that in fact we are not so different from the vegetal world. So I wondered about that, obviously, especially given your study on the brain, which I hope we get to talk about, to what extent would that be the case? To what extent are we similar to the vegetation around us? And where does that limit stop?
Oh, it's a very deep idea, and I agree with that. I mean, we share with the plants one central common fact, that we want to invade the entire planet. We are living beings, and living beings, life in general terms, propagates itself. Of course, it propagates in time, but it propagates also in space. It little by little invades everything. So this notion that life invades everything implies a kind of growth, a kind of expansion. And in order to expand, you need energy. And in order to get this energy, you need basically more oxygen, more air. And the point is that air diffuses very badly inside stuff, in water or in your flesh. The air diffuses very little. And if you want to get more of anything that helps your growth, more of sugar, more of water, more of air, more of oxygen, if you want more, it's better to have branches, because branches can collect more water, more air, more oxygen, can deliver more, or can also remove the wastes like CO2. So if you have a network, a branching network, it's much more efficient. Now, of course, once you've said this very general fact, you turn to more specifics. We don't look like trees. We look like animals. So, but still, if you do our autopsy, I mean, you slice in two and you open the body, you will find mostly trees. The vascular system is a branching vascular system. The lymphatics is a branching system. The lungs is a branching system. The kidneys are a branching system. The prostate, the mammary gland, the salivary gland, the lacrimal gland, whatever you name, it's a branching system, maybe except the digestive tract, which is less branching. Most of our organs are branching organs, much like in plants, and basically for the same reason. For example, if you think of the mammary gland, the purpose of the mammary gland is to feed the baby and to feed the baby with milk. So you need a single output through which the baby is going to suck the milk, but the milk is generated at the apex of the branches, where you have some sort of little leaves, which are the acinus, it's called the acinus of the mammary gland, where all the milk is produced. And then it's collected by little tubes which gather towards the trunk. And so, in fact, the mammary gland is just a cauliflower, and the baby is sucking the milk from the trunk
stem
of the cauliflower, so to speak.
Yeah.
And so is the prostate, so is every time you want to produce a liquid in some quantity, you need a gland, and the gland is basically a tree. So this is also, by the way, why we die of the diseases of these trees, because 40% more or less of the mortality in humans is related to cancer of one of these trees. Just to not even mentioning problems in the vascular system.
Right.
So these branching trees, it's better if they work properly. Just to mention that not everything is perfect happy in the topic of branches. So indeed, many of our supporting organs are branches, and this is why we can get bigger and we can proliferate. Of course, the difference between animals and plants is that we run, we move around, and this is because the fibers of the plants are very static, like wood. By definition, wood is rather static. We make furniture out of it. While animals, they are made of fibers which have evolved contractile activity, and this contractile activity generates the possibility to move, and this is why we are not quite like trees. It's also because during the embryogenesis, this contractile activity tends to fold our tissues into our envelope, which we call an animal. Our envelope, which is our animal envelope, is just a folded piece of tissue, and all these little branches I've been talking about are little branches which grow much like roots in a pot. They try to find their way inside the folds of our body. I'm not sure whether that was clear or not.
Yeah, no, I remember when you showed me, for example, les plis, the folds.
Yes, typically when you
yeah.
fold your sleeve, you can think this is the blastodisc of a human or chicken embryo, and during development something like this happens, and that generates the dorsal folds and the head fold, but you have these little kinks or folds in the tissue, and inside these folds you will have little glandular branches which are going to grow and which will be our salivary gland, prostate and kidney, all our glands that we have inside the body.
So back to then the physics of this biology. There are two things that I want to think about. Is one, the ways in which the realm of possibility articulates itself. So you're saying it's along the paths that are maybe the least resistant that it finds its way and its efficacy. You also mentioned, though, efficacy in terms of economy in our earlier discussion, too. So I'm interested in how that kind of intense and dense economy of matter and energy is able to be produced. I guess that's the magic formula of growth. But the other thing is, I guess I'm also interested in the ways in which this branching also has a finitude inscribed in it, obviously. There's a way in which we're not infinite. I mean, we're constantly growing, as you mentioned, in terms of expansion, kind of in that way. But there's also, we don't grow n'importe comment, no matter, you know, there's a certain realm of possibility that it meets up against.
The point is that when you think philosophically about branches, you tend to think in terms of patterns. So you can invoke patterns, for example, sphere, cube, and you can add branches. But when you think in terms of pattern, you think of something abstract, which has no scale, for example. You know, if you think sphere has no scale, it's a concept, it's an idea. You can think of branches as an idea. Maybe a letter Y is the minimal branch you can imagine. It's just a pure idea. But now, when you look at the actual world, the real world, things, they are not there just as a flash
Aesthetic
or a
form,
projection of an idea.
Yeah.
If something is there, it has grown somehow, it has found its way out. And so it has to invoke or to use some mechanism of growth. And a mechanism of growth implies some material, some energy, some electricity, some gas, some ion, some material that helps or does the growth. For example, if you think of the river, it's not really something which grows actually, but the water is permanently digging, and this ends into a river. But if you think of the little branches in the batteries, it's ions which come and which aggregate to form the metallic branches. If you think of a plant, you have salts, minerals, whatever, which comes from the roots, and from the inside it tends to grow. So you need what we call in physics a flux which arrives at the boundary and which is the incentive for the boundary to grow forward. So this boundary is able to grow forward because there is a flux of something, either from the outside or from the inside. And so as soon as there is a flux is a word, but in science we put maths on the words, and the flux, you can write the flux, the equations of the flux. You have mathematical equations, and then as soon as you start writing mathematical equations, you shift to a more platonistic or Platonician, I don't know how you say, view,
Platonist,
Platonist word, image of the world, more mathematics, and things become idealized. And once you have the mathematics of the fluxes, you can write the equation for the movement of the boundary, and then you realize that the boundary that you have written can be the surface of a plant, or the surface of a crystal, or the edge of the bank of a river. It doesn't matter much in mathematics when you write the equations for something, x and y's. You don't know if the x's are apples or cars or chairs. You know, it works for everything. It's the same thing for morphogenesis of whatever, and it's the same thing for morphogenesis of trees. You can write down the mathematics of the morphogenesis of trees independently of what stuff this tree is actually made of. And you end up with some sort of categories, a small number of types of trees. Basically two types of trees. Trees which branch at the top, and trees which branch at the sides. So basically the only two types of trees. So there is a universality of the trees, as in the same way as there is a universality for spheres, or a universality for lines, or universality for triangles. There is a universality for trees, and then you can go into the details. You realize that inside this universality you can have a lot of instances, a lot of actual realizations, and then the job of a given scientist is to study more his system.
Right. Yeah, no, that makes sense. So, I mean, I have a few places I want to go. One is to think of, we've talked about the relation to poetics, and the kinds of ways in which one could think of science and a poetics that's operative within science, especially, I think, in regards to the work that you do, not only because you yourself are what one could say literarily inclined, that you both write and are interested in literature, but also in the way that you approach, you could say, your scientific paradigms in ways of thinking about how might we think of a different register in which one kind of categorization operates. So, for example, within biology, how might thinking through it within the register of physics permit another kind of, not only a perspective, one could say paradigm, but I like to think of it in terms of a different kind of register to be seen, which otherwise was not previously legible within materiality. So if we think of poetics as a multiplicity of registers, for example, in which one particular articulation allows for it to resonate in various modalities, and the relationship between form and contingency, for example, the ways in which something, you could say, the stability of form, even though I don't think it's that stable, I think that's yet again idealized. But if one could think about that organicity of form within a language, for example, in Old English, you don't really operate with word endings in the way that you do in Latinate languages. It's poetics form kind of interior branches, so to speak, in forms of kennings and different kinds of lines and meters. So I know I'm going on a tangent here, but I'm just thinking about the relation of contingency within dendritic formations. And then the other thing I kind of want to touch on is the differentiation between dendritic formation, or between the arboreal within the vegetal and the animal, and the ways in which the work that you're doing now is really thinking about nerves and muscles and what difference that brings to it. So, yeah.
Well, there are lots of things in what you're saying, and we just see, it's the evidence that trees are something really so dense in the world, that as soon as we start speaking about trees, we sprout out ideas in many directions. So now, the first thing is, when you are a scientist, you tend to do things, your work is not very funny, it's very dry, very formal. It turns out that when you study plants or organs, you generate beautiful science. You have things that you can show, nice pictures. So it's more pleasant. So from this point of view, the science of branches is sort of unfair, because it deals with something which is funnier, nicer, more pleasant, and even maybe slightly more poetic than other sciences like metallurgy or whatever, which are less pleasant. But still, there is something deeper in this question of poetry or poetics, is that when you do science, even science of these nice things, you approach these things with a formalism. So in science, we need a formalism. We can only move forward if we can apply a mathematical formalism even to flowers. And so this is something which sort of resonates with literature, with poetics, because when you write, I happen to write, when you write, you also use a formal language, which is the language, which is by itself essentially formal, but you don't write in the same way when you do poetry, or when you write a scientific article, or when you write law. You have a different kind of formalism. So when you do science, you do things formally, and you expect to do science formally. And it turns out that there is some sort of a surprise, that sort of a resemblance between poetry and science, in that when you do something formal, you expect the formalism to generate something very, comment dire, uniform, and this is not the case. When you do science, even formally, you have a lot of surprise. You have something that jumps out from the formalism, which is very surprising. And this, I think, is the common with the literature, that you write, and at some point, something different, something new, something unexpected happens. And this is I would say, the common point from my point of view of both scientist and a writer, between writing and science. This is for one aspect. The other thing is there were several things.
There were several things.
There were several things. The question of you mentioned the question of the brain, the nerves, the difference between animal and plants.
Right.
So
and the fold, the ways that the folds are differentiated, and your recent work also on the brain and the possibility.
So first of all, one thing that everybody knows, probably, I guess that everybody knows that nerves are branching cells. So many cells are more squarish or hexagonal, and the nerve cells are very much branching. And this is very important, and this is why animals are so efficient. It's because we are made of flesh. Most of our flesh is muscle, okay? And we get big and we can move around. We can get as big as whales and move long distances because we can move very efficiently. And this efficacy of the muscles come from the fact that the nerves have a branching structure. The purpose, the initial purpose of the nerves, because we think of nerves because we have brains and we think that we need nerves for our brains. It's not so. This is not how the nerves evolved. The nerves did not evolve for us to think with them. The nerves evolved for the purpose of digestion, to optimize and synchronize the muscles of the gut. So if you want to synchronize muscles, especially muscles in circles, you need to address all the muscles simultaneously with an electric wave. And if you want the electric wave to arrive at the same moment on all the nerves, the best thing is to have a branching network. And so you send an electric wave, it arrives on the muscles, and the muscles will constrict simultaneously. And this is why we can go to the toilets and have our bolus go from mouth to anus automatically. So the origin of
the brain
is the poo, is the digestion.
Okay.
Digestion. But the point is that when you take nerves and you ask them to synchronize the muscles, you end up with extra nerves which have nothing to synchronize. And so they start talking to each other instead of talking to muscles. Okay? So nerves, you have nerves that go into the muscles, and this is how we move or how we digest. But you have extra nerves which are somewhere in the central part of the body, and they just hook to each other instead of hooking to muscles. And when you have nerves which hook to each other, they start doing interesting things like oscillatory waves, and they end up thinking. So this is for one aspect of the difference between animals and plants. Another difference is that recently we have shown that if you look at the development of plants and you look at the development of animals, they are just identical at the very beginning. Not similar, identical. So the first rounds of divisions are identical, and animals tend to look like a slice of lemon or a slice of grapefruit at early stages. But the difference between animals and plants is that when you think of a grapefruit, you have this whitish fibers which form wedges. The difference between the grapefruit and the humans is that the whitish lines that you see in the grapefruit, they are just fibers, they stick into your teeth and you try to remove them. These, it's dead meat, it's just fibers. While in animals, these little white fibers, they already are minute tendon-like,
contractible.
active, contractible little fibers. So now if you think of a slice of grapefruit or of lemon, and you think that everything white that you see in the slice is a little contractile tendon, and you just let it do its contraction, you end up with a little fish. That's the point. If you take a drawing of circles and wedges and you let it constrict, you get a little fish. A little fish, it's not yet a human, but what is the difference between the little fish and the human, and that was the purpose of my last paper, is that when you take this slice of lemon and you roll it up, the wedges become lines on a tube. So the basic fish is a cylinder with rings, and it turns out that when you balloon out the neural tubes, this tube, it tends to balloon out because you have liquid which is trapped inside, the cephalic liquid. And it turns out that the tube with fibers, when you balloon it out, it becomes a brain. So the brain is not too far from a slice of lemon that you would simply roll up. Of course, I'm waving hands, it's very exaggerated, but if you boil it down to a fundamental epistemology of what is a brain. A brain, it's a birthday balloon which wants to inflate, but
is contracting.
It's hindered by a small number of rings. So one of the rings will make the difference between the cerebellum and the brain. Another of the rings will make the boundary between the hindbrain and the forebrain. So you have a very large variety of things, a lot of instances of branches, lots of brains, lot of animals, but you can always boil down things to very simple concepts. And this is a debate because biologists, they don't like very much the physicists because we tend to explain things by simple concepts. But then when you turn to a specific case, but then how do you treat this disease? How do you explain the giraffe instead of the man? But your explanation is the same for dogs and cats. Yes, but the physicists, they tend to generate a general law, and then, it's hard work to see how each instance can be explained by the general law. There is this saying that Jean Perrin, which is the role of the physicist, is not to explain the existence of each pebble in the streets, but each and every pebble in the street must be explainable by the physics. So voilà.
So I can imagine. So this is just an article that was published, so people know that this was just published last week.
Last week, yes.
In Nature magazine.
In Nature Scientific Reports.
Nature Scientific Reports.
Yes, it's a paper which claims to explain the origin of man, of humans,
not a small
by the laws of physics.
Okay.
It's not by chance. Of course, chance is needed to reach the humans, or to reach the cats, or to reach the jellyfish.
Chance or contingency,
but,
si on peut dire, right?
But there is a mechanism, a physical mechanism, which produces such animals by the physical laws. It's intrinsic to the physical world that there should be animals with a big brain, a face, a mouth, the way we are.
I mean, it sounds a little bit, you could say, a little bit Aristotelian or a little bit, you can think about dynamis, the potentiality being kind of at the root of this, in terms of a potentiality for it's like a belting mechanism that's constricting and producing constantly this way.
We find the animals and plants very odd, and so we tend to think that they appeared by chance. But in fact, the laws of physics produce strange things. So as long as we don't know how strange are the objects that hard science can produce, it's a bit awkward to claim that they appeared by chance, because maybe the plain normal physics can produce very bizarre things. My opinion is that most things are the way they are, not because they were produced by chance. It's just that they are the way they are because nature cannot do things in any other way.
No, I mean, that's interesting, though, because for you, it's not an infinite set of possibilities, although within possibility, I mean, you can see it's like a différence, in the way that Derrida thinks of deferral and delay, ou sein de la langue, on peut dire, that there's a kind of way of generating differentiation.
Yes, in fact, if you look maybe in a sort of visionary way, but a vision towards the back, towards the past, you see that there are very few animals and plants. The number of species is by the million. That's not a lot, There are, I don't know, maybe 30 species of cats. That's not a lot. There is only one species of humans. You keep on finding new humans, but the number of human species that have been found is maybe in the 20s. It's very little. The number of vertebrates, maybe 50,000, no, maybe 200,000. It's not a lot. The number of existing vertebrates today is by 50,000, and for a physicist, they are very small numbers. We are used to dealing with gigantic numbers. The numbers of animal species or plant species is very small. Now, if you think in terms of evolution, you see that it takes millions of years for animals to really change significantly. If you look at humans, maybe we are the way we are only in the last 400,000 years. You would meet Neanderthal, it almost looks like a human. You see the first Homo sapiens sapiens 300 or 200,000 years ago, they were just like us. So it means that animals change very little. They change very little, they change very slowly. And if you think that it takes 1 million years to change significantly an animal, and you think that animals have been around for 500 million years, it means that they changed only 500 times. It's very little. If it takes, if you want to make a movie from a little fish to a man, and you need 25 images per second, you make an image of 20 seconds. Okay. A film of 20 seconds is enough to morph the most ancient fish into a human. And this is what you see when you do embryology. I am a physicist, I do embryology, and what do? We film actually in vivo the development of embryos. And what do we see? Mostly nothing. Nothing happens. We have to accelerate the movie to see what's going on. And when you accelerate the movie, you make a movie of a few seconds, and that is enough to see the formation of an entire animal from scratch. So in fact, in physics, we are used to changing scales to find the proper time scale from a phenomenon. And when you take the proper time scale, the proper scale, you see that animal formation and human formation is something rather simple, not that complex, and which has these dynamics
Sure.
that bring it to some forms which are in small numbers.
So one thing though, okay, so we've been talking about individual species, and we've been talking about things in singular kind of idealized forms. We were thinking about branching, trees, etc., but we haven't really talked about them in groups, a forest, populations, etc., etc. And that brings me to kind of a different question about the ways, for example, in current studies of trees, and people look at the communication, for example, among the roots, the kinds of exchanges, the kinds of ways in which one mother tree, for example, to use Suzanne Simard's work, will then nourish, for example, other trees, or signal somehow, on sait pas, to other trees that there's some encroaching danger, and I just wonder about any larger communal effect that that when you're seeing things in relation to others, does that inhibit that growth? Does it stimulate the growth? In what ways does this coextensive nature of, because it's obviously not growing in a vacuum, not growing in a petri dish. These are things that are.
I think you have two different things.
Duck.
You have actual material networks that you can evidence, be it roots, be it streams of liquids, be it flow of hormones, or so you have networks which sort of mechanically, physically connect things to each other.
Yeah.
So you can think of roots. They have discovered mushrooms which are something like 100 kilometers wide,
right.
or trees which have gigantic roots, or they have discovered a forest in which, in fact, all the trees are the same individual.
Right, like the birch, yeah.
So you can think of a branching connection, not always branching, by the way. Sometimes you have also little loops, anastomosis, little loops.
Oh.
I'm going to this year to a meeting in Canada about networks. It's branching and looping.
Oh, okay.
Looping and branching. So, but branching is very important, and you can always make loops from branches, or you can make branches from loops. If you cut loops, you make branches. So there is a relationship between loops and branches. Okay, never mind. Now, if you can address and study the connection between everything through the physics, the mechanics, the chemistry of all these networks. But my feeling is that there is something else, which is that there is something more abstract, more thinner, difficult to touch, that the entire world, I'm not going to say something mystic, I'm going to say something more mathematical, more statistical, that in fact the world is actually a world of correlations. We have been there together since the origin of the Big Bang. So there is a relationship between everything through space and time. And in fact, it's a little bit like a gigantic internet network, so to speak. And when you do science for some time, as I've done, you realize that the same questions, the same facts, the same concepts are here and are connected to each other, the same ideas. People think to another scientist probably is doing the same research as myself somewhere, and it's just by chance that I publish maybe 1 week earlier than he does, and all of a sudden you are surprised that some team has published the same thing, and so in fact there is a network, a material network, but there is also some abstract network in the world that connects everybody to everybody, and every concept to every concept, and every being to every being by the laws of causality, of correlation, and the laws of causality are a complete mess. I mean, it's completely, it's a very, very difficult to perceive because they are not present concretely. It's just a story, actually. I don't know if that was clear.
No, I didn't understand that one. But
You don't understand?
it's not that it was a story. I could understand how.
You have branching
Right.
in the true world.
Right.
There are hidden branches in the true world,
Right.
like the rhizome, the
rhizome. The rhizomatic. Yeah.
Maybe you won't see it because
Right.
it's in the
Dirt. Yeah.
But there is another branching system that you don't see,
Okay.
which is the branching of history, of correlation, causal correlation by history.
Right.
For example, Richard Feynman, which is a famous American scientist, he solved the equations for quantum mechanics,
Yeah.
and he has shown that you can treat the movement of particles by solving for all the possible would-be trajectories of a particle, and you have to add up and to integrate mathematically all the branching possibilities. But this is in an abstract mathematical quantity in the space of quantum mechanics. And in fact, the world is a bit like that. Every time you do something, it seems that you are moving. You know, when you go through air in a room, you go through air in a city, you are walking, it seems to you that you are walking freely, but in fact, you are walking inside a gigantic web of historical correlations between things that you don't see,
absolutely,
which is somewhere in an abstract world that we don't see. And sometimes it pops out when you realize that a colleague has done the same thing at 10,000 kilometers away from you, or you notice that you're working on a branching system which was already known by an alchemist 1,000 years ago, and you read in a book something that you have almost just written the day before in a scientific paper. So then you realize that I've written that in one of my books, that the world has some sort of a density of correlations, which in fact is not infinite.
Well, as a medievalist, I can say that
the world is finite and limited.
Limited, but I wouldn't want to mistake that with something overdetermined en même temps. You know, it's not necessarily predicted or toujours déjà su ou déterminé, but also as a medievalist, I mean, that's one of the reasons why I don't think that studying the Middle Ages is studying the past necessarily, but there's an interesting way in which, for example, the Arboreal in Northern Europe in the 900s becomes extremely pertinent to the way that we're thinking about the Arboreal today. So I think that I would totally agree, and that legacy, c'est pas du passé, it's not in the past, but rather it's somehow embedded in a very interesting way, even in the materiality of the present. They carry within themselves their own historicities in an interesting way.
I agree, it's embedded.
Yeah.
I mean, most of my colleagues, especially young colleagues, but most of my colleagues, I think they rarely realize how close even modern concepts are to things which have already been discussed, put forward.
Right.
Even Aristotle, he studied chicken embryology.
Aristotle did?
Yeah.
Oh, interesting, huh?
So,
yeah.
We think that we move completely freely, but no, there are little, like a web of things which are immaterial, which have created us, and we are inside it.
You mentioned the rhizome. I mean, there's a big... Deleuze, it's interesting because he really distinguishes between the rhizomatic and the arboreal, characterizing the arboreal as a very hierarchical system, c'est-à-dire Christianity, logic of genealogy, of kind of the hierarchy of knowledge, and a certain kind of structural, and he privileges the rhizomatic in its ability to kind of operate in a more horizontal way. but I think that the way that you're thinking about the arboreal and that I choose to think about the arboreal doesn't necessarily share that kind of distinction. And that even though the rhizomatic might be less visible, the way that you're speaking about the arboreal too is a less concretized or definitively concretized kind of form too.
I think, these shapes or these patterns, they share a common cause, which is conquest. They want
conquest?
Yes, conquest. Sure. They want to, the trees, they want to
grow.
To grow, to be the biggest possible, to have the largest number of...
canopy or whatever.
But the rhizomes or mushrooms, they also have this duty. They need to proliferate.
Yeah.
Simply, there is not a single solution to proliferation. They can reach their goals by different means, even in terms of patterns.
So just one kind of, maybe this is the last question, in terms of thinking biodiversity, because the way that you've described biodiversity would mean it's a not very diverse biodiversity, but that the little that we've got is helping shift around our nutrients, our resources, our oxygen, whatever. Yeah.
Yes. In fact, diversity is a bit misleading or puzzling. In France we have a lot of cheese, we have a lot of camembert, and we have people who collect boîtes à camembert. So we are very good at collecting different boîtes à camembert. They have different sticker, but in fact they are all boîtes à camembert.
Yeah.
And we are very good at finding an interest into minute details which are different. Okay? Now, if you turn to animals, you see that, for example, between vertebrates and arthropods, so between insects and fish, so to speak, you have one major bifurcation, such that, in fact, at the very early stage, the difference between vertebrates and arthropods is that in the first cell, the yolk is sideways in the vertebrates, while the yolk is inside, in the center, in arthropods. And that makes a huge difference that sort of causes in cascade a great number of differences, and eventually people have some sort of feeling that insects are inside-out vertebrates. It has been described like that. So you take a vertebrate and you turn it inside out like a sock, and you find roughly the structure of an insect. It has been known for centuries. But it comes from a fact that at the molecular level, inside the zygote of the arthropod or the zygote of the vertebrate, the position of the yolk is not the same, and this is maybe related to some material difference, just like oil and vinegar that won't mix, and the oil and vinegar in the arthropod and the oil and vinegar in the vertebrate do not have the same viscosity and surface tension. It's probably something like that. That causes the difference. But now, if you go to looking into detail the arthropods, there are maybe millions of species of insects. But in fact, when you look at insects close enough, especially with electron microscope, they look very much alike. They have antennas and they have legs. Okay, but when you look at the antennas, we call it antennas. The antennas. We call legs the legs. But nature doesn't call the things. If you look at the things without naming them, you realize that the antenna is just a small leg. Okay. Now, this makes the pattern of insects roughly universal, uniform. They look very much alike, and it's also true of animals. It's of vertebrates. It's so much true that we tend to make a caricature. How do you say caricature? A caricature of a man into I don't know. A chicken, or a caricature of a man into more a wolf. because they are very much alike. There is even an entire science which is called comparative anatomy, which tells you which part of the man corresponds to that part of the chicken. So in fact, apart from a fundamental bifurcation, all arthropods look very much alike, all vertebrates look very much alike. There is another bifurcation for the gasteropods, but the number of fundamental plans is very small.
Well, I think this is... So the one thing I've wanted to talk about that we haven't spoken of is about the parallel between the poetic and the scientific in terms of, you've spoken of the generative power of dendrites, but also thinking of the poetic and the ways in which it generates, the poetic is it generates meaning. It generates meaning that you can't even circumscribe, that it's... So I think there is a kind of, if you want to call it a logic of the arboreal, but it's pas nécessairement logique, the effect of the arboreal in the way that it's generating some kind of creative play and a kind of interactive play. I don't know, I'm wondering what you think. Right.
Okay. There is something which might be logical or not.
Yeah.
Let me just express a feeling. When you look at trees, you obviously see that there is some sort of conquest. I mean, the trees, they tend to grow and to get bigger and to proliferate. So you look at a given tree, it's something which is conquering its surroundings. Now, if you look at the concept of tree in itself, the entire concept is proliferating. I mean, you have trees everywhere. You end up finding trees. I mean, I walk in the street and I see dendrites in the curbs. Once you've seen trees, there is an inflation, in fact, of even the concept of trees. Okay. So, in fact, there is a creativity of nature, which was very well known of the ancient scientists, naturalists. They tend to ascribe to nature power of creativity. This is how it was called. So they were not very much in a hard science.
Yeah.
It would suffice for them to invoke the creativity of nature. But now, when you turn to questions like hard science and hard poetry, I may say, you find a common creativity. Something happens in science. Scientists will hardly talk about it, but they do talk about it, that when you do the best science of all, once or twice in your life, something happens that when you do something, you search for something, you start to put the correct formalism on a scientific thing that you are studying, something happens out of the blue, which is new, which is amazing,
inattendu,
which is staggering,
right. Yeah.
which is sometimes called serendipitous, which is a ravishment, as Galileo said. It's something absolutely beautiful. And this creativity of science is both logical and illogical, you say. It's something you feel and you can't explain, because it's some sort of aporie. It's
right.
It's the unexpected that you expected, but you
could not
dare not expect,
right.
because if you expect it, it doesn't happen.
Right.
If you expect it, you
yeah.
look for it, and if you look for it, you don't find it, because the truly unexpected thing has to be unexpected. That's the point. So this is why in the scientific academy, we tend to generate the conditions for the unexpected. This is why they do special coffee machines in the coffee room, because we don't know how unexpected things happen, but we know that you have to You have to facilitate, to make things such that maybe if you this biologist would meet that mathematician, something unexpected is going to happen.
Right.
So they try to generate the conditions for the unexpected.
Right.
And it rarely works because the true unexpected things, they really are unexpected. So there is a contradiction between favoring the unexpected as something which is intrinsically contradictory. And this is a common point. This is, to make a long story short, it's creativity. This is how creativity works. It comes out of the blue. But still, you sort of prepare the ground to it, but you don't know how. And I think this is also what happens in literature, and especially in poetry.
Too, also.
In poetry, that you have some initiation. Poetry does not completely out of the blue. You have some formalism. You have a state of mind, and sometimes something pops out, which is poetry, which is an œuvre. Somebody has, I don't know how you say, une œuvre, a work. But I mean really the work as the work of an artist, of a poet. And this is the common between poetry and science, that you have this creativity, and the surprise is that it's never ending.
Yeah, I don't think it would be limited only to poetry. I think even sometimes reading, because aussi your way of reading the materiality at hand, the data, the results, what's happening. There's a kind of descriptive phenomenological moment, but there's something else that comes into it. And as we read the past, as we read its traces, we're not just documenting something, in a kind of banal way. We're also inventing new ways of putting things in relation to each other that we don't see, that we have to imagine in terms of maybe there's a different sensibility at work, maybe there's something else that we can't
Well, in
quite
science,
feel.
we invent in a bizarre way, in that we invent something which already exists, so to speak, which is that we are looking for the laws, how we call it, the laws of nature.
Right.
And we may think that we know all the laws of nature, but in fact we still find serendipitously new things which are a surprise and which help to understand the world. I remember I was once at a colloquium at the UNESCO, and there was a Nobel Prize, and he gave a lecture about particle physics, and he ended his lecture saying that with the next accelerator of particles, we would know the ultimate frontier of science. So more or less, science was finished, game over, we have finished. We are going to know the next boson, and the story will be over. And then another Nobel Prize who was in the audience, Walter Kohn, he stood up and he said, no, there are other frontiers. Okay? And so, yes, there are other frontiers, and we're still looking for them. And the fact is that in science, when we look for the frontiers, we are at the frontiers, but we don't know where exactly is the next step. And more often than not, this step, we stumble on things. There is this word, I think it's Flaubert, who said, quand la science avance d'un pas, c'est qu'un imbécile l'a bousculé sans faire exprès. And so we happen to make things move forward
by accident.
I myself was studying the effect of electrical stimulation on development, because I want to try to stimulate the development of fingers, of the development of hands for children who have malformations or accidents, to try to regrow fingers by electric stimulation. and I ended up stimulating embryos, and embryos are very small, so we ended up stimulating the head of embryos, and we discovered that when you stimulate the head of an embryo, at small values of the potential, it winds backwards towards the lizard, the chicken, and at higher values of the potential, it winds forwards towards being more human-like by electrical stimulation. So it's a complete shock.
Haphazard, yeah.
It's a shock. So, voila, it's by accident, you stumble on something which is unexpected, but I realized that I myself, I've been expecting this my entire life, actually. Because my own father was some sort of amateur anthropologist, so I realized that I've been waiting for something like that without knowing it.
Well, I think this gives a lot to think about in terms of what our concept of nature is. Our concept of the human is differentiation from, why don't we have the vegetal and the muscular rather than humans and nature? But it has a lot of profound philosophical implications in the way that you think about it. And I think we can probably end with that as a final thought, and hopefully to be continued, maybe in New York. Maybe we can work that out next time.
Très volontiers.
Okay, super. Okay.
Thanks a lot.